Actually, two-dimensional spectroscopy, the idea comes from NMR, but I don't need to talk about that. And has been developed with ideas from NMR. The theory is basically the same. And then has been developed for infrared spectroscopy, where you can follow vibrational modes. And here is that's a very good review on the method itself. So if you, in this case, you have some vibrational modes of acetone, whatever, and if you have two oscillators, two transitions, and they are not coupled to each other. In the 2D spectroscopy, you have two frequency axes. One corresponds to the pump, and the other corresponds to the probe. So it's basically the same story, but you resolve also the pump and the probe separately. Now, if you have two uncoupled vibrators, you excite one vibrator, one oscillator, you will have a signal at its frequency, and then with the probe you will probe the same frequency, so nothing interesting happens. Then another molecule you may have in the solution that has or another group in the molecule that has a different transition frequency, different vibrating frequency. You will see it at some other point, but they will always be, if they are not coupled, they will always be on the diagonal where the pump and the probe frequency is the same. However, if they two are talking to each other, if they are coupled, then you can pump at one frequency and probe at the frequency of the other, and you will see a cross peak or correlation. So the 2D signal is actually a two-point correlation plot. Correlation between two coupled frequencies. And in this case, it doesn't matter if you couple one, if you excite one or the other, you will always see the transition, the signal as the corresponding coupled partner's frequency. So you can tell from here, the 2D spectroscopy gives us information about which molecules are coupled together, which molecules can transfer excitation energy to each other. It's basically the same thing. Now, that's why, as you will see, it is very useful to follow and to map energy transfer between different molecules. So how do you do the two-dimensional spectroscopy? Now, okay, I will mention that what you said in the beginning, people did double resonance, right? So this means how you can do in the double resonance experiment, you will use narrow frequency pulses, and you will actually excite one transition with a very narrow pulse that will not cover the other one. So your pump will be narrow pump, and your probe can be narrow or broad, doesn't matter. And then you can scan. So change the frequency of the pump, and then put them all together, and then you have another dimension. Yeah, you can do that. However, that's not what you would want to do, because first of all, there are many, if you go into the nonlinear theory of the signal generation, you will see a lot of artifacts from here. I will not talk about that. But the most important problem is that if you have a very narrow pump, Fourier transform limit dictates that you will have very long pulse, brought in time. So if you gain spectral resolution, you must lose temporal resolution. I mean, this comes from Heisenberg and from the Fourier transform. And what we need is temporal and high spectral resolution. And this, you can kind of cheat the Fourier transform limit if you use broadband pulses and you use time domain two-dimensional spectroscopy. What is the real two-dimensional coherent spectroscopy done nowadays everywhere? In time domain, you use, instead of narrow frequency pulse, you use a pair of two very short pulses with broad, spectrally broad. Then, what you do is you set a time between these two pulses, and I will explain a little bit more about that. Now, first of all, this is nonlinear spectroscopy, right? This is third order nonlinear spectroscopy. That means the sample will interact with 3 laser pulses. And in pump probe, which is also third order nonlinear spectroscopy, but never mind. In pump probe, we use one pump and one probe. And in the 2D, what we do is we split the pump in two, then we have the probe. And third order means this is a 4-wave mixing, maybe somebody has heard the term 4-wave mixing, in which we get a photon echo signal. And actually people used to call two-dimensional spectroscopy photon echo. Now, why do we create these two pulses? What do they do? They do this. We have now, as I said, 1, 2, and 3, actually 3 delays. Delay between the first 2 pulses, delay between the second 2, and delay between the third and the signal. This delay is called coherence time, and this is called waiting time or population time. What happens in the coherence time? The first pulse interacts with the sample and creates a coherence. What is a coherence? It's so what happens when the pulse interacts with the sample is we create coherence. It means a superposition of quantum states, where one is, let's say, one is the ground state, one is the excited state, and the system will oscillate between these two. Because when we have a superposition between two eigenstates, the system will oscillate between the two. The wave function will have this periodic oscillation, which has the frequency of the transition, right? The transition has a certain frequency that corresponds to the frequency of the laser pulse, or the absorbed photon, if you wish. Although the theory here is not about photons, it's about electric fields and field interaction with the field. So we have oscillation. So the sample will oscillate here between the two energy levels, let's say. And then with the second pulse, if the second pulse comes in phase, the system will interact with it. If the second pulse comes out of phase with the oscillation, it cannot see the system. So the second interaction will be small. So which means if we vary the delay between these two, we can see periodic oscillation at the end of the signal. This is one. Now, this oscillation, as I said, corresponds to the frequency of the transition. It means if we then make a Fourier transform, that means from time domain we convert, just like in FTIR, just like in Fourier transform, spectroscopy, linear spectroscopy. We Fourier transform over this time, and we get the frequency of the oscillation. That means the frequency of the absorber, of the absorbing molecule. Then, from then on, it's just pump probe. Then we wait for some time for the system to evolve, energy transfer, photochemistry, and so on to occur. And then we send the probe pulse, and we detect the echo. And in pump probe, the echo is also, the system will emit a signal with some frequency. Or in frequency domain, it will absorb certain frequency. And in this case, in how we do in the visible optical, in NMR, people also do this in time domain. You can follow the signal in time, but we cannot do that in femtosecond regime. What we do here, we just send the signal to our spectrometer, which does exactly the same. It does Fourier transform. It resolves the frequencies in our signal. So at the end, we have two frequencies. One is called omega 1, frequency 1, and one is called omega 3, or frequency 3. That will be the frequency of the pump, and that will be the frequency of the probe interaction. So the signal is then, just like in pump probe spectroscopy, we have the frequency, time, and another frequency. Now, how do we do it in practice? There are several ways to do, but what we've been doing, and it's probably the simplest technically, is we just use a normal pump probe spectrometer, and we have, as I showed you before, we have our narrow band pulses, we have our broad probe, we have a delay somewhere here, we have our modulation, and then we focus them onto the sample, and then the probe will be frequency resolved on the spectrometer. And what is the difference? The difference is only one small device, which is in this case acoustic modulator, so-called pulse shaper, which allows us to split the pulse into two. So we have, from one pulse, we create two pulses, and just with computer control of the pulse shaper, we can set these pulses apart. We can program the delay between them, and we can program the phase of the pulses. You know, light has also phase. We need that. And then we have a two-dimensional spectrometer. So what we need to do to get the two-dimensional spectrum is just we have to sweep over this time between the two pulses, scan over a certain range with certain steps, and then we get oscillations, and then we just Fourier transform our signal. From time domain we get frequency, right? And then we just plot it. So then when we plot it, we can put one frequency on one axis, the other on the other axis, and then we have this correlation plot, or the 2D spectrum, what we call 2D spectrum. So what do we learn from it? Now, if we go back to the LHC2, oh, in 5 minutes, and right?
35.
Huh? Sorry?
35.
35 minutes?
Okay.
I don't think so.
25.
Yeah, okay. Okay. Thank you. I don't have so many slides to fill. I only fill one. Okay. So what do we learn? I just want to show you the example of the LHC2. Basically, that's the method. Let's say we have two chlorophylls, or whatever, two molecules. So one has a higher transition, the other has a lower energy transition. We pump at one transition, then we allow some time for energy transfer to occur, then we probe at both. So what we will see diagonal peaks. Now, we have broadband pulses, right? So they cover all frequencies. And in the two-dimensional spectrum, we will see the one, let's say the A molecule or energy level, we will see the B energy level. If there is the energy transfer from one to the other, we will see a cross peak. Simple as that. Okay? Now, if we follow that in time, because we are doing transient 2D spectroscopy, this cross peak, A and B, will follow in time the dynamics of the energy transfer. And so by following the time, the kinetic trace of the cross peak, we can tell what's the rate of energy transfer and so on. And here is the actual two-dimensional spectrum of LHC2 evolving in time. This is the same experiments like I showed you with the transient absorption. Here we excite chlorophyll B and we see what happens. So chlorophyll B absorbs at 615 nanometers, and that is here. So that means in the beginning, at time 0, we have the chlorophyll B signal, and you can see that it very quickly disappears. And at the same time, you can see the chlorophyll A, this cross peak, will appear. Now, in this experiment, our pump does not cover chlorophyll A, only the chlorophyll B bands. So we don't see the diagonal peak of the chlorophyll A here. We only see chlorophyll B to chlorophyll A transfer. So just I pause this, and you can compare two spectra at, let's say, half picosecond and at 5 picosecond, and you can see at half picosecond you still see the chlorophyll B, you see some chlorophyll A, at 5 picosecond no more chlorophyll B, some chlorophyll, everything is on chlorophyll A. Okay, this you can also see in pump rock. But now we have the extra dimension, it gives us additional spectral resolution, and it also tells us, for example, here, this part of the signal came from chlorophyll B's absorbing at this wavelength. Here, it came from chlorophyll B's absorbing at this wavelength. So we can tell not only where energy is, but also where energy came from. Right, so we can plot here, for example, here with what we have plotted, the chlorophyll B decays, like you saw in the transient absorption, the chlorophyll A rises, and here is a 665. This is the middle part of the spectrum. You can see one part rises. In the beginning, the signal rises, and then it decays. So, and there is a correlation here. As one decays, the other rises. So what actually we see? We see two steps. We see chlorophyll B transfers to this frequency, which is intermediate frequency, and then this frequency will decay on its turn and transfer to the lowest energy chlorophyll. So we can see stepwise energy transfer. And we can also tell, I will not spend time on this, but you can then plot for one chlorophyll frequency the coupling with chlorophyll B's, which only comes from the second dimension that we have, and see some differences. Then what you usually do when you have any kind of time resource spectroscopy, you want to do some quantitative analysis, and so we do some fitting to get some rate constants, some physical parameters from there. What we do is what we call global analysis. That is, we take every point in the spectrum and fit its time evolution with some exponential components, and this is done globally, so all of them are linked. Then we get a set of lifetimes which are common for the whole system, and we get the pre-exponential amplitudes, are what we call 2D decay-associated spectrum. And this, that just allows us to see very easily the energy transfer partners, where when you have this energy transfer, one will decay and we'll have a red spot, the other will rise at the same time, and we'll have a blue spot. So we can see that from here, energy goes here. And these are actual decay-associated spectra. I'm not going to tell much, but we can see on different time scales, that intermediate state here, different states transferring energy from here to here, and so on. So that's how we analyze our data. This is another example where we have now our pump covers chlorophyll A molecules. And now, if you look at the pump probe signal, you won't see much, nothing happens. But only you will see the decay of your signal. But here we can see very nicely the spectral evolution. This is the raw signal, this is fitted by global analysis, and you can see that the spectrum evolves in time from this diagonal shape, it becomes a circle, and as the energy is equilibrated between different chlorophyll A's. And what you also see, this is very interesting, that now you can see this part, this cross peak tells that energy came from 665 nanometers and went to 680. But at the same time, we can see a little bit, but you can see it, energy can start from 680 and end up at 665. So energy can go both ways. It can go downhill, but it can also go uphill, because this is done at room temperature, physiological temperature, where we have enough thermal energy to drive everything also backwards. So if we do the same global analysis, we can see the relative changes of, we can see, as I told you, the energy transfer partners. So, for example, on this time scale, you can see this frequency transfers energy down. At the same time, the energy can go from the low energy states back to the high energy states. So we can see both the forward and the reverse reactions in the 2D spectrum, which you would never see in a one-dimensional spectrum, because you don't have this frequency dimension. So then, when you put all this together, you can fit the lifetimes, and you can get the reaction scheme in your network of pigments. And if you then compare with so what we do is then we validate the theoretical models and test them, and then we can tell which reactions correspond to which pigments and so on. So in 5 minutes last, I will just mention you that we can also do 3D spectroscopy, and it's not so complicated as a concept. It is complicated to do in practice. As a concept, it's very simple. If we can split our pulse in two and make 2D spectra, why don't we make another pair of pulses and make another Fourier transform, and then we will add one more dimension. And then we have 3 frequency dimensions, 3-dimensional spectrum. Now this is 5th order spectroscopy. The signal is very weak, but you can do it. So it's very similar in concept to the 2-dimensional, but now we have 1, 2, 3 frequencies, and because we have 2 coherence times, we Fourier transform over this. This is normally frequency resolved. So we have 3 frequency axes and 2 time axes. So we also have 2 population times where we allow the system to evolve. So why do we do that? Because, as I showed you, and it's very clear, energy transfer is not from donor to acceptor, it's from donor to somebody else until it reaches the final state. So it's a multi-step. And it's still, even with 2D, it's quite difficult to follow all these steps. Now in 3D spectroscopy, we can actually say, what if we excite one pigment and then see if it transfers to the second and then to the third? Can we directly follow this 2-step reaction? And yes, that is exactly what we follow with the 3D spectroscopy. So the signal only satisfies the condition that energy started at the first frequency, then over time T2 went to the intermediate frequency, and then over time T4 went to the final frequency. This is just showing exactly the same. So we use exactly the same machine, we use the same pulse shaper, only computer control. But that's simplification. Because then you need to extract the actual 3D signal from all sorts of other signals, because we send 4 pulses to the sample, but we cannot tell the sample that it should interact one with this pulse and one time with this and one. It can interact 4 times with the first pulse and not see the other at all. Or it can interact 2 times with this and 2 times with this and not with the other, all combinations. So how we can do that? How we can tell the system to interact once with each pulse that we dumped at it? We do that by what is called phase cycling. We not only sweep the time delays between the pulses, but we also sweep the phases of the pulses, and then we know the exact dependence of our 3D signal on the phase of the pulses, and then we can, with the proper phase cycling, we can extract the signal. But that's another story. So here's what we can see. That's a 3D spectrum, 3-dimensional spectrum of LHC2. And what we see here, lambda 1, lambda 3, lambda 5. And here is, for example, one 3-dimensional cross-peak. This is not interesting at all. This is just where everything is the same. It means where we excited, there we probed on the diagonal. That's not interesting. But what is interesting is outside of the diagonal, where the energy actually went somewhere else. So here, for example, this is a 3D cross-peak, but it's too much information, right? You cannot tell anything from here. What we do is we take a slice, we cut the spectrum at some point, let's say at 655 here, and on this slice, we can see that 3D cross-peak as a small spot here. So now you can see a very tiny spot, which corresponds to a single pigment, single exciton state actually. And we can follow that in time because we impose so many restrictions. This spot is only there if the energy started on this pigment, then it went to this one, and then finally it went to the lower energy state. And we can plot this in time and get the rate constant of energy transfer and so on. So there you go. We reached the summary. So in 2D, as you saw, we extend the traditional pump probe spectroscopy by adding another dimension, frequency dimension, which gives us direct correlation between the frequency of coupled electronic states. And we can also see in the 2D spectra not only downhill but also uphill energy transfer in the same measurement. Then with 3D, we can follow multi-step energy transfer pathways, and we get a unique spectral resolution that is not possible by any other means currently available. And as I said, this we cannot do yet in Szeged, but we have a very good, strong, long collaboration with Nanyang Technological University, where we can do all sorts of these spectroscopies. So now is your time for questions. And thank you for your patience. Right. Too much information.
So what you can actually evolve from this regarding that in which direction, what orientation actually the first signal chlorophyll spreads? So can you
Exactly, yes. Basically, depends on which is your first chlorophyll. But let's say if we take one pair of chlorophyll beads here, and then we can tell that it is, let's say this will be that one. It will go very fast towards this intermediate state, but it will also go very fast towards the final state. So actually, when you take this all into take the big picture, you will see that there are direct routes from almost any energy level down, because the energy wants to go as fast as possible to the terminal state. So wherever we look, we always see direct routes down, but we also see intermediate routes where the energy really can circle around the whole complex. So,
what is the distance between the two pigments?
the shortest distance is about 6-7 angstroms.
6, 7.
But the longest are tens, hundreds.
And between them is vacuum, or there's some
Protein,
protein.
which is not drone, but
Okay.
it's full of protein.
Do you think there's some solvent molecule is present in?
Yes. The solvent molecules are actually quite important,
Yeah.
but very difficult to exactly quantify. Now, this part is where the membrane is, and on the outer surfaces, there is a lot of solvent. Solvent means water. Okay?
Yeah, of course.
So there's a lot of water and salt, salty water. So, cations, basically, because the surface is negatively charged. But it's important because the lowest energy chlorophylls are actually these three here, which are on the top. And they can feel the water molecules, and they can sense the environment. And that is why this complex is so interesting. I did not talk about that, but it is because it can sense the environment and switch itself off, and then turn itself back on when it's needed. And we don't know how it does that.
These two-dimensional electron spectroscopy, you are not able to detect the effect of the solvent. Because, if you use some two-dimensional infrared spectroscopy, you can see the hydrogen bonding, reformed and break and breaking.
We are just now starting a project to use tryptophan probe, which will be incorporated into the lipid membrane, and it can sense the water. And because the vibrations of the tryptophan, when it is interacting with what we want to see is the water vibrations itself. But we will use the tryptophan as a probe for that, and to see the interaction of the solvent, but with the lipid. And with the protein, I don't know of any real study on this protein with the salt and the water. I mean, on a physical chemical level, only very indirect. Lots of very old studies, but we don't know.
And by using this two-dimensional electron spectroscopy, I think you're not able to see some vibration, some electron transfer, because you mentioned first part is energy transfer, the second part is electron transfer, right?
No, the electron transfer, you can see charge transfer by the appearance of it. We don't expect charge transfer much in the antenna, but you can see the radical pair. Sometimes the appearance of the radical pair will give you a signal, bleaching signal. But you need somebody who is able to do that. I mean, a photochemically active site. This is another project that we are trying to introduce environment on one of the chlorophylls to stimulate it to eject electron. Then we can probably make a reaction center out of the complex. This is only our wish. We have not achieved that.
Most interesting topic for me is science.
Yeah. Yes, you have a question.
I guess that if you have this mechanism of a adjusting the delay
Yeah.
in picoseconds. And we have shown this. You can also try to do depth resolved information from 6 samples. All these samples are thin, aren't they?
We use samples in solution. So these are just in a quartz cell of 1 millimeter thickness to have a small optical pathway. But these are solution based mostly. I'd like to do on solid surface two-dimensional spectroscopy, but we have not done it yet.
I gather that if the sample is thick, wouldn't that induce some error in your delay measurements?
Yeah, of course, but the beam is focused to about 40 microns, and the overlap then is the square. The overlap of the two beams. Then it's a very small, actually, volume where the signal comes from, and it is beyond the resolution. I mean, less than the time resolution. The time resolution is only dictated by the temporal width of the pulse and the convolution of the pulse with actually the walls of the cell, which gives us non-resonant coherent artifacts. But that's about, these pulses are about 50 femtoseconds. So, as you see, I don't plot anything under 200 femtoseconds because we start to get artifacts there.
What is the concentration, the protein concentration used?
Like in transient absorption,
Very high.
but okay, we have a little more stringent here for the 2D because you can get some cascading and stuff. So usually you don't want to have OD more than 0.3, so 50% transmission.
Because the concentration, if it is very high, then maybe there's some quenching between.
Oh no, we are much below that.
Okay.
So much more diluted. You have to be in, first of all, in linear Petar Lambrev
Yeah.
regime. So, and quenching is much more concentrated. But it's a point that one has to take always, a technical point that you need to consider.
Yeah. We found if we increase the concentration of pigment very high level, even it will influence the lifetime measurements.
Of course, yes. If the pigment in solution gets beyond the critical concentration, it will do collisional or excimer quenching. The lifetime will drop.
In order to measure the IR spectrum,
Yeah.
we have to use
Sorry.
So
Too bad.
Yeah.
For you, avoid water.
No, but we don't avoid water.
That's then a problem.
Use TBS buffer.
Yeah, then that absorbs, and then you need concentrated sample. Okay, so congratulations on finishing your